All right, welcome to the final notes of this unit and this semester. How exciting! Today, we are going to talk about how intermolecular forces of attraction impact the state or phase of matter. Phases of matter are going to come up in semester 2 a lot, and the type of molecule you're dealing with can actually help you figure this out. So, this is 4.5 IMFAs and phases. All right, we're going to make a big chart. We love charts. Well, I love charts. You have to deal with them. So we're going to do the bond type. We're going to say IMFA. We're going to do polarity. We'll do phase at room temp. Phase change. And energy required. Like I said, you're going to jump more into these concepts in second semester, so this is just a preview. Okay, there are 3 intermolecular forces of attraction where the bond is a covalent bond. So I'm actually going to save the first column until we get through all 3 of those. And I'm going to go for 2 lines. I said save the first column. Okay, like this. 1, 2, 3. All right, let's go in order of IMFA strength. So an LDF. These are nonpolar molecules. And at room temperature, LDF molecules, nonpolar molecules, are gases. They're a gas. And they evaporate the fastest. You're going to do a lab simulation where you look at this, and there is very low or little energy required to make a nonpolar molecule evaporate. Next up, we have a dipole-dipole. And this happens with polar molecules. And polar molecules can be a gas or liquid at room temperature. They will evaporate or melt quickly. And they require some energy to do so, but it's still pretty fast. My last one is hydrogen bonds. And hydrogen bonds are in polar molecules. And they are usually liquid at water temperature. Think H2O. That's our best example of a hydrogen bonded IMFA. And they evaporate or melt more slowly. And the reason that happens is because the attractions between the molecules are much stronger, so it's going to take more energy to break those attractions and get that molecule to melt or evaporate. All 3 of these, I'm going to turn my page sideways, are covalent bonds. So we have covalent bonds up here. And then our last one, I made my chart too big, but it's ionic. Remember, all ionics are polar. And they're solid at room temperature. We talked about that back when we talked about their properties. They melt very slowly and require the most energy / heat in order to get that ionic solid to melt. A few quick additional notes, and then we are done for today. Some notes here. To melt or evaporate, which means change phase, you add energy. That makes sense. If you're trying to melt ice, you need it to get warmer. Warmth is energy. The stronger the IMFA, the more energy you need to break the attraction, and the more time it will take to change phase. The other thing that accounts for this is that atom size also plays a role. Remember, that's atomic radius. Also affects phase. So, like if we look at column 7 on the periodic table, fluorine and chlorine are smaller. So they are a gas at room temperature. Bromine is larger. It's a liquid at room temperature. And iodine is the largest of this example set, and it's a solid at room temperature. All right, that's it. You've reached the end of first semester notes, so make sure you take a picture of your notes, submit it, and wrap up all of your work for this unit.